Welcome! In this session, we're tackling problem number 1287, element appearing more than 25% in sorted array. This problem challenges us to identify an element that appears more than a quarter of the time in a sorted array. Let's explore the key concepts and strategies to solve this efficiently. Ready? Let's dive in. In this problem, we are given a sorted array of integers, ARR, which contains n elements. Here, n is guaranteed to be at least 1. Among the elements in the array, there is exactly one element that appears more than 25% of the time. Our task is to identify and return this element. Now, because the array is sorted, any element that appears more than 25% of the time will naturally be grouped together in a contiguous block of indices. This characteristic simplifies the problem, as we can focus on these grouped elements to determine the one that meets the condition. The input for the problem is the sorted array ARR, and the output must be a single integer that appears more than 25% of the time in the array. For example, consider the array ARR equals 1, 2, 2, 6, 6, 6, 6, 7, 10. The length of this array is n equals 9. To determine the threshold for 25% of the array, we calculate 0.25 * 9, which equals 2.25. This means any element that appears more than 2 times in the array satisfies the condition. Looking at the array, we see that the element 6 appears 4 times, which is clearly more than the threshold of 2. As a result, the output for this example is 6. Now, let's look at another example. Suppose the input array is ARR equals 1, 1, 2, 2, 2, 3, 3, 3. Here, the length of the array is n equals 8. Calculating 25% of n, we get 0.25 * 8 equals 2. To meet the condition, an element must appear more than 2 times. In this case, the element 2 appears 3 times, which satisfies the requirement. Therefore, the output for this input is 2. Another example is ARR equals 1, 1, 1, 1, 2, 3, 4, 5. With a length of n equals 8, the 25% threshold remains 2. In this array, the element 1 appears 4 times, which is greater than the threshold. So, the output is 1. To summarize, the output for the last example is 1 because it appears 4 times, exceeding the 25% threshold. Moving on, let's discuss the problem's constraints and edge cases. The array length, ARR length, can range from 1 to 10,000, and its elements lie between 0 and 100,000. Additionally, the array is always sorted in non-decreasing order, and exactly one element will meet the condition of appearing more than 25% of the time. As for edge cases, consider an array with only one element, like ARR equals 5. Here, the single element constitutes 100% of the array, so the output is 5. In a uniform array where all elements are the same, for instance, ARR equals 7, 7, 7, 7, the output is that repeated element, 7. Lastly, note that if an element appears exactly 25% of the time, it does not meet the condition. For example, in ARR equals 1, 2, 3, 3, 4, 4, 4, 5, the element 3 appears exactly 25% of the time, so it is not the answer. The correct output in this case is 4, as it appears more than 25% of the time. To solve this problem, the first approach we can consider is the brute force method, which focuses on counting frequencies. The intuition here is simple: since the array is sorted, identical elements will appear consecutively. We can iterate through the array and count the frequency of each element by comparing it with the next one. As soon as the count for any element exceeds 25% of the total array size, we return that element. This method has a time complexity of O(n), as we traverse the array only once, and a space complexity of O(1), since we don't use any extra data structures. However, while straightforward, this approach has its drawbacks. Repeated comparisons can make it inefficient, especially if implemented in a naive way. It's a good starting point but not the most optimal solution. Another approach we can explore is the sliding window method. The sorted nature of the array allows us to use a window of size n/4, where n is the total number of elements in the array. The key insight here is that any element appearing more than 25% of the time will occupy a contiguous window of size n/4 or larger. By iterating through the array and sliding this window, we can efficiently check if the first and last elements in the window are the same. If they are, then that element is our answer. This approach also runs in linear time, O(n), and uses constant space, O(1). While it requires slightly more bookkeeping compared to brute force, the logic is still intuitive and avoids unnecessary repeated comparisons, making it a more efficient choice overall. Now, let's consider a more advanced strategy, the binary search approach. Here, we take advantage of the sorted property of the array to narrow down our search. If an element appears more than 25% of the time, its positions in the array will span at least n/4 indices. We can directly check specific positions like n/4, n/2, and 3n/4 to identify potential candidates. Once we find a candidate, we verify its range in the array using binary search. If the candidate's range is greater than n/4, we return it as the answer. This method combines the power of binary search, which has a logarithmic time complexity, with linear verification. However, while binary search is elegant, it might be overkill for smaller arrays and doesn't provide a significant performance advantage over the sliding window approach. The sliding window approach is ultimately the most practical strategy for this problem. It achieves the right balance between simplicity and efficiency, leveraging the sorted nature of the array to avoid unnecessary computations. The key observation here is that any element appearing more than 25% of the time will occupy a contiguous block in the array. By focusing only on a window of size n/4, we can pinpoint the target element without needing additional data structures or overly complex logic. While the brute force method is too inefficient due to repeated comparisons, and the binary search approach adds unnecessary complexity, the sliding window technique stands out for its clean and efficient implementation. It fully utilizes the problem's constraints to deliver an optimal solution with linear time and constant space complexity, making it the best choice overall. To tackle this problem, we need to identify the integer that appears more than 25% of the time in a sorted array. The guarantee of exactly one such element simplifies our task, as we know there's always a solution. The brute force approach leverages the sorted property of the array, which ensures that all occurrences of the same number are grouped together. This allows us to count consecutive occurrences efficiently. First, we initialize some key variables, n, the length of the array, threshold, which is calculated as n/4 to represent the minimum frequency an element must surpass to qualify, and current_count, which starts at 1 and keeps track of how many times the current number has appeared as we iterate through the array. These variables form the foundation of our approach. With our variables initialized, we start iterating through the array from the second element, at index 1. For each element, we compare it with the previous one. If it matches, we increment current_count, as the current number is repeating. However, if the current element differs from the previous one, we check if current_count exceeds the threshold. If it does, we can immediately return the previous element because it satisfies the condition of appearing more than 25% of the time. If not, we reset current_count to 1 and move on to the next number. After finishing the loop, there's one final check. The last element of the array might still be the one that meets the condition, so we verify if its current_count exceeds the threshold. If it does, we return it as the result. Ultimately, this ensures that we evaluate every possibility in a single pass. This algorithm works efficiently due to several key insights. The sorted property of the input array ensures that all instances of any given number are grouped together, eliminating the need for extra memory like hash maps to track frequencies. Instead, we simply compare adjacent elements to count occurrences. The threshold is calculated as n/4, which directly corresponds to the problem's requirement that the target element appears more than 25% of the time. By checking if current_count exceeds this threshold during traversal, we can determine the result in real time. Another advantage is that the algorithm only requires a single pass through the array, resulting in a time complexity of O(n). With no additional data structures required beyond a few variables, its space complexity is O(1). This combination of efficiency and simplicity makes the approach well suited for this problem. Analyzing the algorithm's complexity, we see that its time complexity is O(n), where n is the size of the array. This is because we traverse the array just once, performing constant time operations for each element. The space complexity is O(1), as we only use a few variables like current_count and threshold without any extra storage structures. Now, let's consider potential edge cases. For very small arrays, such as those with only one or two elements, the condition is trivially satisfied by the first element. In the case of uniform arrays, where all elements are identical, the algorithm correctly identifies the unique number as the result. Finally, even in large arrays where a frequent element appears near the end, the algorithm's final check ensures that no cases are missed. These considerations make the solution robust across different scenarios. To better understand the algorithm, let's walk through an example. Consider the input array 1, 2, 2, 2, 3, 3, 3, 3, 4, 4. We begin by initializing the key variables. N is 10, since there are 10 elements, threshold is calculated as 10/4 equals 2.5, and current_count starts at 1. During the iteration, we first compare the second element, 2, with the first, 1. Since they differ, we check if current_count, which is 1, exceeds threshold. It doesn't, so we reset current_count to 1 for the next number. Now, as we move through the array, we see that the occurrences of 2 are contiguous, and current_count increments to 3. When we encounter 3, which differs from 2, we check current_count again. This time, 3 exceeds the threshold of 2.5, so we return 2 as the result. The final output for this example is 2. This confirms that the algorithm correctly identifies the element that appears more than 25% of the time in the array. By leveraging the sorted property of the input and using an efficient single-pass approach, we've solved the problem with minimal computational overhead. This concludes the walkthrough of the example and demonstrates the effectiveness of the algorithm. This solution leverages the fact that the input array is sorted, which simplifies the task. The key observation is that if an element appears more than 25% of the time, then it must span at least n/4 positions in the array. This means that for any such element, there must exist an index I such that ARR I is equal to ARR I plus n/4. 1. The code starts by determining the length of the array n and calculates the threshold n/4. 2. It then iterates through the array from index 0 to n threshold. The iteration stops early to ensure that we do not go out of bounds when checking ARR I plus threshold. 3. For each index I, the code compares the element at ARR I with the element at ARR I plus threshold. If they are equal, the element ARR I is returned as the answer since it satisfies the condition of appearing more than 25% of the time. 4. The solution guarantees an answer because the problem statement ensures that there is exactly one such element. However, a redundant return statement, return-1, is included for completeness in cases where the problem constraints are violated. This approach has a time complexity of O(n), because it involves a single pass through the relevant part of the array. It also has a space complexity of O(1), as no additional data structures are used. This makes the solution both efficient and elegant for the given problem constraints. This is the Java implementation of LeetCode problem number 1287, element appearing more than 25% in sorted array. The solution leverages the fact that the array is sorted, iterating to check if any element matches the one located at an index offset by the threshold. If such an element is found, it is returned immediately. Key differences from Python include explicit type declarations and syntax adjustments for loops and conditions. The logic remains identical to the Python implementation. To tackle this problem, we are given a sorted array and need to identify the integer that appears more than 25% of the time. The sorted property of the array allows us to solve this efficiently by leveraging the fact that any element meeting the threshold will have duplicates within a specific range. For example, in the array 1, 2, 2, 2, 3, 3, the first step is to calculate the length of the array, which is 6, and determine the threshold, which is 1/4 of the array length, 6 divided by 4 equals 1. This tells us that if an element appears more than once within any sliding window of size 2, it meets the condition. Next, we iterate through the array, comparing each element at index I with the elements separated by the threshold. Starting at I equals 0, we compare ARR 0 equals 1 with ARR 1 equals 2. Since these values differ, we move to the next index. At index I equals 1, we compare ARR 1 equals 2 with ARR 2 equals 2. This time, the values are the same, which means the element 2 appears at least twice within the threshold window. Since we've found the required condition, we return 2 as the result. This demonstrates that the algorithm identifies the correct element as soon as it finds a match, without needing to continue further. Now, let's look at another example. For the array 1, 1, 2, 3, 3, 3, 3, we start by calculating the length of the array, which is 7. The threshold, being 1/4 of the array length, is again 7 divided by 4, which equals 1. This means any element appearing consecutively within a window of size 2 satisfies the condition. We then iterate through the array, comparing elements at index I with their threshold-separated counterparts. At index I equals 0, we compare ARR 0 equals 1 with ARR 1 equals 1. The values match, indicating that the element 1 appears consecutively within the valid range. As such, we immediately return 1 as the output. The process stops as soon as we confirm the condition, ensuring the solution remains efficient. Let's now consider another example with a different sorted array 10, 10, 10, 20, 30, 40, 50. Here, the length of the array is 7, and the threshold remains 7 divided by 4, which equals 1. Once again, we iterate through the array, comparing each element at index I with the element located one position ahead, based on the threshold. At index I equals 0, we compare ARR 0 equals 10 with ARR 1 equals 10. The values are identical, which means the element 10 satisfies the condition of appearing more than 25% of the time. Therefore, we return 10 as the result. This example highlights how the sorted property of the array ensures that any qualifying element will appear consecutively within the threshold range, allowing us to find the solution in a single pass. The algorithm runs in O(n) time complexity, as it only makes one pass through the array, and the problem guarantees a solution exists, so we can confidently stop as soon as we find the match. This makes the method both efficient and reliable, leveraging the sorted nature of the input to simplify the search process. The time complexity of this algorithm revolves around 3 primary operations. First, the threshold calculation involves determining n/4, which is simply a single integer division and takes constant time, or O(1). Next, the main part of the algorithm is the iteration through the array. The loop runs from I equals 0 to n threshold 1, which essentially corresponds to n/4 iterations. This simplifies to O(n), since the number of iterations grows linearly with the size of the array. For each iteration, we perform a constant time comparison between ARR I and ARR I plus threshold, so the work done per iteration does not increase with input size. Finally, the return statement is executed once when the condition is satisfied, which is also O(1). Since the loop dominates the overall runtime, the algorithm's total time complexity is O(n). When analyzing space complexity, the algorithm is highly efficient because it uses only a constant amount of extra memory, regardless of the size of the input. The input array ARR is given and requires no additional space allocation by the algorithm. The variables used, such as n to store the size of the array, threshold to store the computed threshold value, and the loop variable I, each occupy a fixed amount of space, or O(1). Importantly, no additional data structures or memory allocations are introduced during execution. Therefore, the overall space complexity of the algorithm is O(1), which is the minimal possible memory usage for a problem like this. To better understand the efficiency of this solution, we can compare it to a naive approach. A brute force method might involve counting the occurrences of each distinct element in the array, potentially using a dictionary or frequency array. This would require O(n) time to traverse the array and count frequencies, plus an additional O(k) to identify the maximum frequency, where k is the number of distinct elements. In the worst case, k could approach n if all elements are unique, leading to O(n) time and O(n) space complexity. On the other hand, the current optimized solution leverages the fact that the array is sorted. By avoiding the need for frequency counting and additional data structures, it achieves the same O(n) time complexity but reduces space complexity to O(1). This makes it significantly more efficient in terms of memory usage, especially for large inputs. Now, let's break the algorithm down into its best, average, and worst-case scenarios. In the best case, the element that appears more than 25% of the time is found early in the loop. Practically, this could mean less time spent iterating through the array, but asymptotically, the time complexity remains O(n), because the loop structure assumes the potential need to traverse a significant portion of the array. For the average and worst cases, the algorithm may need to iterate through almost the entire array to find the required element, which firmly results in O(n) time complexity. From a mathematical perspective, the single traversal of the array ensures that each operation scales linearly with the size of the input, while memory usage remains constant throughout the process. This guarantees O(n) time and O(1) space complexity in all scenarios. When working with this problem, there are several common mistakes to watch out for. First, many candidates assume the array is unsorted, even though the problem explicitly states that it is sorted. This leads to missing opportunities to optimize the solution using techniques like binary search, which can significantly reduce the time complexity to O log n compared to O(n) for linear approaches. Another frequent issue is failing to consider edge cases, such as arrays with fewer than 4 elements. For these smaller inputs, calculating percentages like 25% may not make sense, and this can result in incorrect outputs or even runtime errors. Next, overcomplicating the solution is another pitfall. Instead of leveraging the array's sorted property, some candidates unnecessarily introduce hash maps or other advanced data structures, which add complexity without improving efficiency. Finally, errors in percentage calculation, such as using floating point arithmetic instead of integer math for indices, can lead to subtle bugs. Always use floor division for precise calculations, especially when determining thresholds like 25%. Another error to avoid is using inefficient brute force traversal methods, like nested loops, to count element frequencies. This can result in an O(n)² time complexity, which is excessive when more efficient techniques, like a single-pass scan or binary search, can solve the problem faster. Now, when preparing for interviews, there are some key insights to keep in mind. First, always understand the constraints of the problem. If an array is sorted, consider whether binary search or similar efficient methods can be applied. Problems involving sorted arrays often have logarithmic solutions, so this is a critical optimization opportunity. Additionally, focus on testing edge cases. Scenarios like small arrays, arrays where all elements are the same, or arrays where no element meets the 25% threshold are situations interviewers often expect you to handle correctly. It's also important to discuss trade-offs in your approach. Clearly explain why a brute force solution is inefficient and why you prefer an optimized method, such as binary search or sliding windows. Finally, optimize your logic during the planning phase before jumping into coding. Recognizing the array's sorted nature early and designing a solution around it showcases strong problem-solving skills. This problem is closely related to several others on LeetCode that also involve identifying majority elements or leveraging sorted properties. For example, in LeetCode 169, majority element, the goal is to find the element that appears more than n/2 times in an array. Similarly, in LeetCode 229, majority element 2, you need to identify elements that appear more than n/3 times. These problems focus on majority thresholds but differ in their specific constraints. Another related problem is LeetCode 1150, check if a number is majority element in a sorted array, where you determine if a given number appears more than n/2 times in a sorted array. This problem emphasizes working with sorted arrays, making it highly relevant here. Lastly, LeetCode 240, Search a 2D Matrix 2, deals with leveraging sorted properties in multidimensional arrays. While the context is different, the problem-solving techniques share common themes, such as optimizing for efficiency by taking advantage of sorted data. To solve this problem, you can explore several alternative approaches, each with its advantages and trade-offs. The binary search approach involves locating the potential starting position of any element that could appear more than 25% of the time. Once found, you verify whether its frequency meets the condition. This method is highly efficient, with a time complexity of O log n for the binary search step, plus O(1) for the frequency check. However, it requires careful implementation to ensure correctness. Another option is the sliding window approach, which tracks the count of consecutive elements as you traverse the array. If an element's count exceeds the threshold, it can be returned as the result. This method is simpler to implement than binary search, with a linear time complexity of O(n), but it may not be as optimal for extremely large arrays. Finally, the hash map approach counts element frequencies during a single traversal and returns the first element exceeding the threshold. While easy to implement, this method has a higher space complexity due to the use of the hash map, making it less space efficient compared to binary search or sliding window techniques. Each approach has its strengths, so choose based on the problem constraints and your implementation preferences. Great job! To summarize, we solved problem number 1287 by leveraging the sorted nature of the array to count element frequencies effectively. Remember, sorted data can simplify many problems, so always consider how to use that advantage. Thanks for joining, and don't forget to subscribe for more problem-solving insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!